Okay, so we're going to start the next section, which is 3.4, and I'm just going to call it, this is like the general section is going to be on number theory, but I'm going to call this section the division algorithm and modular arithmetic. And we're going to be going, we're going to be breaking this up into a few videos, at least 2, if not 3. 5, 7, 9, and 19, because really division algorithm is kind of one thing and modular arithmetic is kind of another. They are definitely related, but I'm definitely going to be splitting it up at least a little bit. So there's a laundry list of topics in this section. We've got divides, multiple, factor, we've got Theorem One, and I'm going to say no proofs of all parts. We've got Theorem 2, which I'm going to call the division algorithm, and we don't need to know the proof of the division algorithm. It's definitely within the scope of this class. I used to teach this in this class, but it takes us just far enough outside of where I think most of your computer science students, most of you probably don't need to know that much detail. So I've sort of trimmed that out, but it's definitely worth looking up a proof if you're interested. If you're not interested, don't worry too much just yet. We've got congruence modulo m. We've got Theorem 5, and you need to know proof of part 1. I'm going to let you slide on the proof of part 2. Proof of part 2 is not much harder than the proof of part 1, but there's a little trick, and I don't like testing people on tricks. I don't think that's very classy if I can avoid it. Next, we're going to talk about z sub m plus sub m and times sub m. All right, so let's get into it. Given integers a and b, we say a divides b if there exists an integer k such that b equals ak. Now this should look familiar because we say that 2 divides b if there exists an integer k such that b equals 2k, right? So we've already discussed even numbers, that is when 2 divides a natural number or an integer. So now we're doing a more general divisibility criterion. All right, so now we write, if a divides b, we write a vertical bar b and say b is a multiple of a, and this is something that you've almost certainly heard before. And a is a factor of b. So these are, again, things that you've almost certainly heard before. So let's do a couple of quick examples. Okay, does 3 divide 17? No, it does not. 3 does not divide 17 because 3 doesn't evenly divide 17. That is, if I put 17 inside the house and 3 outside the house, I get a 5 here and a remainder 2, right? There's a remainder. Okay, different example. 4 divides 12. And this is because, so these are, I guess this doesn't really imply one or the other. I'm just saying these are equivalent here. And that's because there exists 3, which is an integer, such that 4 times 3 equals 12, right? All right, so now let's use these for our first theorem. I'm going to call this Theorem 1. And this is for all a, b, c integers with a not equal to 0, the following are going to hold. So 1, a divides b, and a divides c implies a divides b plus c. Part 2, A divides B implies A divides BC. And part 3, A divides B and B divides C implies A divides C. We're going to prove these. All right, so each of these are going to be proved in a really similar fashion. That's why they're all kind of lumped into one theorem. And the way it's going to work is I'm going to write down the hypothesis in just in less dense language. So, and then I'm going to draw a conclusion from it. So this is more than a theorem that's important. This is practicing writing down hypotheses and drawing conclusions. So, proof of part 1. A divides B implies what? Let's go to the definition of A divides B. A divides B if there exists an integer k such that b equals ak. If there exists an integer k such that b equals ak. All right, cool. Now we also have that A divides C here. A divides C implies, no, we already used k, so we're going to say there exists an integer L such that C equals AL. Okay, just use a different number, or sorry, different letter. And I'm using a script L, or like a cursive L, because we've already got a vertical bar. So this is a vertical bar, this is a 1, this is an L. These are absolute value bars. You know, it's getting a little scary, so I'm using a script L there. Now, remember what we do when we've written everything down that we know. What we're going to do is we're going to imagine that we're at a really cool party. And what do we do at a really cool party? We consider quantities. We're going to consider the quantity b plus c. Well, b plus c is equal to ak, I'm substituting in, plus al. And now I can factor out an a and get a times k plus l. And this is of the form a times an integer. So a divides what? A divides b plus c. Now, how do I know that k plus l is an integer? That's because the integers are closed under addition. Okay, that's just something that, you know, that's an axiom that we accept about the integers that I'm not being super specific about. But remember, it matters that k plus l is an integer, but maybe k divided by l is not an integer. Okay, let's try to do part 2 now. Part 2 is a divides b, we know that, and that means there exists an integer k in z such that b equals ak. It's the same as before. So now what do we need to do? Well, we're all out of hypotheses for part 2. We now need to go after the conclusion. Let's look at the right-hand side of the conclusion here. There's b times c. Now we consider bc. Right? Well, bc is equal to, let's write out, akc, which is a times an integer. So I've just shown that bc is a times an integer, which means a divides bc as claimed. Okay, and again, like I think I've mentioned, these little diagonal lines just sit at the end of a part. Now let's try to do this third part here. So for part 3, I've got that a divides b. Well, that implies that there exists an integer k in z such that b equals ak. Now I've also got that b divides c. Oh, and if you're wondering, each of these parts is separate. Okay, 1, 2, and 3 are all separate. So it's not like I have a divides b and a divides c, and all of a sudden this is this is a different c. Okay, it's not like these are the same a, b, and c across parts. All right, not necessarily. It's just that I'm lumping these all together and saying a, b, and c are integers, but the c from this part isn't necessarily the c from this part. All right, and that's, if you're wondering why does he keep writing out this same first line over and over again? It's because think of this as different functions. And if I have the same variable names across different functions, that doesn't mean that they're doing exactly the same thing. All right. So now I've got b divided by c, which means there exists an integer L such that, Such that c equals BL. All right, now I consider c. Well, c is going to equal, we just saw, b times L, but b is AK, so this is AKL. Well, this is A times an integer. And that implies that A divides C as claimed. So now we're done with the proof of Theorem 1. I would recommend pausing, going back, and rewatching this before you get too far behind. Okay, the last thing that I want to do here is I want to state a theorem, and then I want to talk about it a little bit. So Theorem 2, and this is what I'm calling the division algorithm. There are many things called the division algorithm. Depending on which mathematician watches this, they might get sick to their stomach when they see what I'm calling the division algorithm. This is just to get a point across to students in this class. I'm going to say for any a and d integer with d non-zero, there exist unique integers q and r such that, and I know you're like, wait, two unique things? You'll see. Q is unique as q, r is unique as r. There exist unique integers q and r such that 0 is less than or equal to r, which is strictly less than the absolute value of d, and a equals qd plus r. And that's the division algorithm. And what you might be saying right now is, hey, look, there's no division, and it's not an algorithm, and that's a completely fair critique, okay? So this is a theorem which provides the central sort of engine for why the algorithm that we use for division works, right? So I'm going to go into some long division, and we're going to be applying this result over and over again. So let's just do an example, and then we'll come back and see how this relates to the division algorithm. Let's look at 137 divided by 5. Okay, so I'm going to write 5 here outside the house. I'm going to put 137 inside the house. And I say, how many times does 5 go into 1? Well, it doesn't, so I don't do anything with them. And I move on over. How many times does 5 go into 13? Well, 5 goes into 13 2 times. 2 times 5 is going to be what? 10. I subtract. 13 minus 10 is 3, right? And then I bring down this 7, and I've got 37. How many times does 5 go into 37? Well, 5 goes into 37 7 times, and I've got 5 times 7 is 35, and I subtract. 37 minus 35 is 2, and I don't have, I could do decimals and keep going, but instead I'm going to stick to integers here, and I'm going to say that this 2 goes up as remainder 2, like, I did this example here earlier. It's a similar situation. Okay, so now what I want to do is I want to express this relationship compactly. So what I'm going to do is I'm going to write 137 equals 5 times 27 plus 2. So this remainder, you notice, has to be between, I guess I've got Q and D switched the way that I wrote it here. Still true, just maybe to be a little bit less confusing. So this remainder is definitely less than my divisor in absolute value. Also, for the sake of our class, these are going to be naturals. I'm just showing you a statement. But, if I tried to do a long division problem and I came up with like 8 here, we'd know that I had messed up somewhere because 8's bigger than 5, right? So this number has to be between, it could be 0, but it's between 0 and this number here, the divisor. Dividend, divisor, I can't remember the names of these things. Then I also have this tells me how many times this number goes in here at most, and then there's maybe some left over. So this division algorithm is what's making this calculation and this calculation at each step. It's a theorem, it's not an algorithm, but it's a theorem that's used in an algorithm for division, so I guess that's where it got the name division algorithm. Anyways, we're going to